Hey guys, in this video we're going to talk about 1B from linear algebra done right, definition of vector space. Okay, so before we talk about what a vector space is, we need to talk about a notion called closure. So here's the definition. We say that a set, okay, so a set is just a collection of elements. And in this case, our elements, we're going to call them vectors. Okay, so we say that a set is closed under vector addition if when we add two vectors, so if we add two things in the set, we're still in the set. Okay, that's what it means to be closed under addition. So let's look at an example of something that's closed under vector addition. So our set S is going to be the set of ordered pairs where x and y are both real numbers and x and y are both bigger than 0. They're both positive. So we can think about this set as just being everything in the first quadrant, right? So, we can think about it like this. Here's our x-axis, here's our y-axis, and anything in this set is going to be in this first quadrant right here. Okay, and this set is going to be closed under vector addition because if you add any two things in the first quadrant, you're still going to get x and y being positive. So for example, so how about we say let x, y, how about we say this? Let A, B, and C, D be in S. Then A, B plus C, D is going to be equal to A plus C. We just add component-wise, comma, B plus D. And since A was positive, we said it was an S, so A and B are both positive, as are C and D. Since everything's positive, when we add two positive numbers, we're still going to get a positive number, right? So this first component's always going to be positive, and likewise with the second component. We're adding two positive numbers, so it's always going to be positive. We can look at a more like concrete example. So like if we actually assign numbers to the coordinates, we can say 1, 2 plus 3, 4. These are both members in our set because both x and y are real numbers and they're both positive. So they're in quadrant 1. When we add them together, we get 1 plus 3 is 4 and 2 plus 4 is 6. This is also positive. So any two vectors where your x and your y are positive, when you add them together, you're still going to get a positive answer. That's what it means to be closed under addition. It means that addition is not going to kick anybody out of the set. Okay, so now that we looked at an example, let's look at a non-example. So this time our set is all ordered pairs where x and y are real numbers and x and y satisfy this equation right here, x squared plus y squared equals 1. Now, what does that mean? Like, what does the set actually look like geometrically? We saw geometrically that our set in the first example was the first quadrant. But what does this set look like? Well, you should recognize this from like pre-algebra or algebra class as the equation of a circle centered at the origin with radius 1. So if we were to plot S, so this was S in the first example, and here's S in our second example, it's still a subset of R2 because it's x comma y, so points in the plane. And this time we're going to make a circle of radius 1. My drawing's not the prettiest, but whatever. So this is it. This is our set. Just this red piece is our set right here. Okay. And the question is this closed under addition? If we add any two vectors on the circle, are we still going to get something on the circle? Is there going to be something on the circle? Well, not all the time, right? Because what if I take a specific example? So maybe pause the video at this point and try to find two ordered pairs that are on the circle, but when you add them, the sum is not on the circle. Try to do that right now. Okay, so how about this one? This is 1, 0. This is on the circle because 1 and 0 are both real numbers, check, and 1 squared plus 0 squared is indeed equal to 1. So yeah, that's on the circle. For a similar reason, negative 1, 0 is also on the circle, right? Negative 1 squared plus 0 squared does indeed equal 1. So those two are on the circle, but their sum is not, right? So if we take negative 1, 0 plus 1, 0, we add these guys component-wise, so negative 1 plus 1 is going to give me 0, and 0 plus 0 is going to give me 0. This is not on the circle. This is not on the circle. That's the origin. And the origin is going to be right here. So we see that it's not on the red piece, and so this guy is not closed under vector addition. In a similar way, we can say whether or not sets are closed under scalar multiplication. So scalars are just numbers, and when we say a set is closed under scalar multiplication, we need to say where our scalars are coming from, and that it depends on what our field is. So our field, our F field, is where scalars come from. So, for example, the set R2, we can think of it in two ways. We all know what R2 is. It's simply, let me do this in black actually. It's simply the two-dimensional plane. So here's our y-axis, here's our x-axis, and R2 is everybody. So that's R2. We can also think of R2 in like set notation. We can say R2 is just the set of ordered pairs where both components are real numbers. So that's R2. All right, so any point that you can think of on the plane, any x comma y, where x and y are real numbers, it's going to be in the set R2. And R2, so ordered pairs are closed under multiplication by real numbers, right? Because if we take lambda is a real number, so lambda can be any real number, and multiply by something in R2, we get, well, so let's say lambda xy, where x and y are real numbers, then we get lambda x, lambda y. So this lambda x is in R, it's in the real numbers, and so is the lambda y. And therefore, this guy is going to be an R2 because the first component is a real number. Real numbers times real numbers are themselves real numbers. It's just a field axiom. And same thing for the second component. A real number times a real number is also real. So this is multiplying by a real number is not going to kick anything out of the set. Okay, so anything in the set R2 multiplied by a real number lambda is still going to be in the R2 set. We're still going to have a real number in the first component, real number in the second component. So that is closed under scalar multiplication. Okay, let's look at a non-example. So how about the integers? So if you've seen this before, great. If you haven't, it's okay. The integers, sometimes we use this little weird looking z to indicate that we're dealing with integers. And that's just going to be whole numbers, positive and negative. So like -2, -1, 0, 1, 2, ... and ... going that way too. Okay, so those are integers, whole numbers, positive and negative, and 0. The field that we're dealing with, where our scalars are coming from, are going to be the real numbers. Now think about what the real numbers include. Real numbers include many more numbers than integers. And the set of integers is not closed under scalar multiplication by the reals. So not closed under, so the integers are not closed under scalar multiplication by the reals, because an integer times a real number isn't always an integer. We'll get kicked out of the set in some cases. For example, how about 2, which is an integer, times square root of 3, a real number, is equal to 2 square roots of 3, which is not in the integers. Okay, so the integers, using scalars from the reals, it's not closed under scalar multiplication. Okay, so that's the idea of closure under vector addition and scalar multiplication. So now we come to definition 1.19 in the book, vector space. So a vector space is a set, V, capital V, that is closed under vector addition and scalar multiplication, and the following properties hold. So commutativity, this is, this isn't the most fun part of linear algebra, but it's something that you have to go through and learn about to get to the more interesting stuff. So let's just go through it, and once we do this and verify all the properties for a few vector spaces, we'll never do it again, and it'll be nice. So okay, commutativity. We have two vectors, u and v, and commutativity means that we can reverse the order that we add them in. So u plus v is equal to v plus u for all vectors u, v in our vector space. Associativity means that if we're adding up three vectors, we can shift around the parentheses. So parentheses u plus v plus w is equal to u plus and then parentheses v plus w. And we can also shift the parentheses when we are scalar multiplying. So when we have scalars a, b times a vector v, we can rearrange the parentheses in this way. Additive identity means that there is an element 0. It doesn't necessarily have to be the 0 that we know and love, but there is an element 0 so that when we add 0 to a vector, we're going to get that vector, right? So, you can think of, with real numbers, if you take a number and you add 0 to it, the number 0, you're going to get the number that you started with, okay? The real numbers turns out to be a vector space. Additive inverse, so for every vector in our vector space, there's some other vector so that when we add them, we get 0. So this, again, you can think of like your real numbers, -3 plus 3, or 3 plus -3. There's an additive inverse there. And, we're going to get more abstract, so we're not necessarily dealing with real numbers, but in a vector space, all vectors have an additive inverse. Multiplicative identity, this is pretty straightforward as well. 1 times v equals v for all vectors in your vector space. So multiplying by a scalar 1 isn't going to change your vector. And the distributive properties that we know and love also apply to vector spaces. If we have something, a scalar a, and we're multiplying on the outside by the sum of 2 vectors, we just distribute how you think you would distribute a times a vector u plus a times a vector v. And same thing with our v on our right side. Our vector v on our right side, we can distribute the v in from the right instead of the left. Okay, so distributive properties hold. Now let's talk about specific vector space examples. Now the real numbers are a vector space, as I just mentioned. This is a one-dimensional vector space, and all of these things hold. So we don't prove that these things hold. The real numbers are a field, so we take all of these things to be true already, and we use the fact that they're true in the real numbers to extend the definition to higher dimensions, R2, R3, and in general, Rn is a vector space over the real numbers. So what does that mean? You can have a list of n elements, so, x1, ... all the way to xn. This is a vector in Rn. And what we're going to show, which, again, this isn't exactly the most thrilling thing in the world to verify these things are true in Rn, but just to get your feet wet, with vector spaces. These are very, this is one of the most simple vector spaces, Rn. We're going to talk about more abstract ones in just a little bit, but let's get our feet wet here. So we want to show that Rn is a vector space. So here's our proof. So let's say we want to show, let me do this in black. So we want to show that Rn is a vector space. And so for the first one, is it closed under addition? We need to verify that. I'm not going to go through every one of these, but I'll go through most of them just to show you how this goes. So closed under addition. How do you show that Rn is closed under addition? Well, you want to start by introducing 2 arbitrary vectors in Rn. And to show that their sum is going to be in Rn as well. So what we're going to do is we're going to say let x1 ... xn and y1 ... yn be in Rn. Okay, so we wrote down 2 random lists. We didn't give specific numbers. We just said, okay, x1, xn and y1, yn are in Rn. That means that each xi, so x1, x2, all of those things are going to be real numbers, and same thing with each y1 all the way to yn. Those are all real numbers. So we said, okay, there's 2 vectors in Rn. Now we're going to add them. And we talked about how to add vectors last time. We just add them component-wise. That's how we do it. So x1 plus y1 is simply x1 plus y1. x2 plus y2 is x2 plus y2, all the way to xn plus yn. Okay, so we added the 2 vectors, and by the properties of real numbers, x1 plus y1 dot 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 all the way up to xn plus y1 are real numbers. So Rn is closed under vector addition. Okay, so we've just shown closure. And how did we do it? We said let two arbitrary vectors be in Rn. When I add them together, by the definition of how I add vectors, I get this. And since I assumed that x1 all the way through xn and y1 all the way through yn were real numbers, I assume that here. The sum of real numbers is always a real number. And so x1 plus y1 is real, all the way up to xn plus yn is real. So therefore, this guy, this vector right here, is in Rn, right? Because we have n real numbers in a list. All right, closed under addition. How about closed under scalar mults? Well, remember our scalars are coming from the real numbers. When we say vector spaces over something, that's our scalars. So over R, so scalars are R. Again, we start with an arbitrary vector from Rn. So let x1 dot 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 xn be in Rn. And let lambda be in the real numbers. So that's our scalar. Multiply. We have lambda times x1 dot 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 xn. Just by definition of scalar multiplication, we distribute that scalar in to give us lambda x1 dot 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 lambda xn. And again, I'm writing every little step out, but you don't have to if this makes sense to you. Since lambda x1 dot 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 lambda xn are all real numbers, right? Because a real times a real is always a real, are all real numbers. Then lambda x1 all the way to lambda xn is in Rn, right? Each of these is a real number, and so it's in Rn. So we've just shown that Rn is closed under vector addition and scalar multiplication. So that's the first. I told you guys this is a little bit annoying to do this because it's like, come on, this is annoying. But I just want to make sure you guys know how to do this for more complicated examples. Okay. Let's see. All right, so let's look at the next guy, which is commutativity. And again, I'm not going to do all of these. I'm going to let you try associativity. And I'm going to let you try multiplicative identity and distributive. But I'll do the rest. Show you how it's done. Okay, so let's look at commutativity. How do we show that Rn vectors in Rn commute? Okay, under addition. So how do we do this? Well, again, we want to start by introducing two arbitrary vectors in Rn. So we want to show that they commute. So let x1 dot 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 xn and y1 dot 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 yn be in Rn. We want to show that x1 dot 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 xn plus y1 dot 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 yn is equal to y1 dot 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 yn plus x1 dot 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 xn. So we want to show this to show commutativity. So this is not too bad. So by definition of vector addition, we have the following. We have x1 dot 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 xn plus y1 dot 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 yn is equal to, well, we just add the components, right? So x1 plus y1 dot 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 xn plus yn. Okay? So that's this side. Now what about the other side? And again, by vector addition, y1 dot 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 yn plus x1 dot 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 xn is equal to y1 plus x1 dot 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 yn plus xn. And these things almost look alike. Now, we assumed that each of these yi's and each of these xi's were real numbers. That's what it means for this list to be an Rn. It means that each of the entries are real numbers. So since that's the case, real numbers commute, and I'll put that in parentheses here. Real numbers commute. That's an axiom that we're going to assume. Okay, so real numbers commute. I can't spell. That's fine. So real numbers commute, so this means that we can switch the order in the little entries. So x1 plus y1 dot 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 xn plus yn. So check it out. Now they're the same. So commutativity is proved. Or is shown, whatever. Sweet. Okay, so we did commutativity. That's done. I told you guys to try associativity, because if I went through each one of these, gosh, you guys would be so bored. You'd never watch a video again. So try the associativity and the 6 and 7 yourself. I'm going to do additive identity. All right. So what does that mean? And actually, I'm going to erase some stuff because I'm running out of room. So additive identity, there exists something, some vector that acts like 0, so that when we add it to any other vector, we get the vector itself back. Okay. And we just need to show that it exists in Rn. We don't really need to say, I mean, we say why it exists, but all right, I'm going to stop talking. Let's go up to here and let's say, okay, so we're going to now do additive identity. So, take a vector, an arbitrary vector in Rn. Does there exist a vector in Rn so that when we add it to x1 dot 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 xn, oops, we get the vector back. So is that true? Is there a list of numbers in Rn so that when we add it to this guy, we're going to get that thing back? And the answer is yeah. It's just 0, right? N zeros. So our answer, or our additive identity, is 0, ... 0. So this is the first 0, first, and this is the nth 0. Right? We can't just add literally the number 0 to a vector because we don't define addition that way. We don't just take a number and add it to a vector. We need a vector to add to a vector. So that's why we have to have a list of zeros versus just a regular 0, right? Because we take this vector, we add the additive identity, which is just a list of n zeros. And if it helps you when you're trying to get your feet wet with proofs, try to maybe do this in 2 dimensions. So n is equal to 2. That means we have 2 zeros. In 3 dimensions, n is equal to 3. That means we have 3 zeros. And you can think about it like that. So when we take a vector and add the additive identity, we get x1 plus 0, ... xn plus 0, which is simply x1 ... xn, because the additive identity in real numbers is the number 0. So that works. That's our additive identity. And why does it exist? Because zeros are real numbers. We have a list of n zeros. That's definitely an Rn, for sure. Okay, so that's taken care of. Last one I'm going to verify for you guys is the additive inverse. So the additive inverse. So does there exist a vector in Rn such that when I add it to x1 ... xn, I get the 0 vector, or the additive identity? And maybe pause the video and think about if there is such a vector that exists in Rn, so that when you add it to x1 to xn, you get the 0 vector. Yes, it exists. And it is the following vector: negative x1 ... negative xn. Why does this exist? Well, we, by assumption, x1 through xn are real numbers, and this vector x1 to xn exists. If I multiply each entry by a scalar, negative 1, we already verified that this is closed under scalar multiplication. So this is certainly in Rn. So this certainly exists in Rn. So we have x1 ... xn plus negative x1 ... negative xn. Well, when we add these guys, we get x1 plus negative x1 ... xn plus negative xn. And we all know how to add real numbers like this. This is just going to give us 0 ... 0. So again, this first entry is the first 0. This guy is the nth 0. So this is our additive inverse of x1 ... xn. All right, so that is how you can verify that something is a vector space. In this case, we verified that Rn was a vector space, but again, if it helps you, try to do it for R2 first and then R3 to get your feet wet. But, in order for this to be complete, you do need to verify associativity as well as multiplicative identity and distributive properties, but these aren't hard, and you should try these on your own. Is Rn a vector space over the complex number, so where the scalars are complex numbers? And is Cn a vector space over the real numbers, where the scalars are real numbers? Okay, so we can tell easily whether or not something is not a vector space, usually with the closure axiom. So are vectors closed under vector addition? Is the space closed under scalar multiplication? So for the first one, we know that any two real vectors is going to be real. So closed under addition is okay. However, is this space closed under the scalar multiplication? So no. So not closed, not a vector space, first of all, because it's not closed under scalar multiplication. Where our scalars are coming from C. And why is this? Consider the vector 1, 3. I'm just making up one in R. We could say Rn. We could change that to R2 just for simplicity's sake. Let's do that. So is R2 a vector space over C? No. Consider 1, 3 in R2. Multiply by the scalar I. Now I is an imaginary number from the complex numbers. That's a valid scalar because our scalars are in C. So if we multiply by I, what we're going to get is I times 1, 3, which is I times 3I, and this is not in R2. Remember, if it were, then both of these entries would have to be real. So this is not a vector space over C. However, Cn is indeed a vector space over R. If we add two complex vectors, we're still going to get a complex vector. Scalar multiplication is okay as well because multiplying a complex entry by a real number is not going to kick it out of being complex. Remember, complex numbers include the real numbers and more. So yeah, and you would have to, you'd have to verify all of the axioms if you wanted to, like commutativity, all the other stuff. But I'm not going to do that here, but you can do that as an exercise, verify commutativity, associativity, all of that stuff. So yes, Cn is a vector space over the reals. Okay, so this is 1.23 in the book, notation f to the power of capital S. So S is going to be our set, and f to the power of S denotes the set of functions from S to our field F. So that's the notation. So for example, R to the 0, 1, that means that our functions take on values, take on inputs, I should say, from 0 to 1. So functions take in inputs from 0 to 1, and the outputs are going to be real numbers. So that's what this notation means here. This is the way that we define function addition in FS. The sum f plus g is just going to be f of x plus g of x for all x in our set S. And if we have lambda in our field and f is a function in fs. The product lambda f is defined to be lambda f times x is equal to lambda fx for all x in our set. So that's just how we define these things. So let's take a look at some more examples of vector spaces. As I mentioned, vectors don't have to be lists of numbers. This is a more interesting, I guess, vector space. The set of functions that take on values from 0 to 1 and output values of real numbers. So real valued functions on 0, 1. This is a vector space. And we can check a few of these axioms. I'm not going to check all of them just because that would take too long. But closed under vector addition, certainly. Why is that? Well, just by the way that this addition was defined in the previous slide. So yes, we have f plus g of x. So adding two functions from the space, f plus g, is going to give us f of x plus g of x. And this is going to be a real valued, or a real number, so a real valued function on S. So definitely closed under addition. Also closed under scalar multiplication for a similar reason. Yes, and this is by the way we defined this multiplication. We had lambda f x is equal to lambda f of x. And this is a real valued function. On 0, 1. So definitely closed under scalar multiplication as well. So you can check commutativity, associativity, multiplicative identity, and distributive properties. So check those. Again, this take way too long to check all of these, but the idea with this example is that, hey, vectors don't have to be lists of numbers. We can have functions being vectors. So that's interesting. What about the additive identity? Well, that's just going to be the 0 function. So 0x is our additive identity, and it equals 0 for any input, for any x in 0, 1. So for all x in 0, 1. That is my additive identity. If I add this function to any other function, I get that function back. Additive inverse is going to be negative f. So if I have a function f in this space, then negative f is going to be the additive inverse. Okay, so, I'm kind of glossing over some details here, but yeah, I would check the commutativity and everything like that just to convince yourself that R to the 0, 1 is indeed a vector space. Now here's a really simple vector space, and it simply consists of the 0 vector. If you want to not confuse yourself, maybe put a little arrow above that to say, hey, that's the 0 vector, and it's not just going to be the number 0 unless your vector space is like the real numbers. But yeah, so that's the 0 vector, and this is like super easy and trivial to verify these axioms. So I'm just going to talk about them, I guess. Closed under addition. Well, yeah, because if we add the 0 vector to itself, we get the 0 vector. Duh, right? Closed under scalar multiplication. Yeah, because a scalar from the reals, I didn't really specify my field, but it doesn't matter. The scalar times the 0 vector is always going to be the 0 vector. So that's closed under scalar multiplication. Commutativity. Yeah. 0 plus 0 does equal 0 plus 0. Yeah, and it's like super obvious, right? So all of those axioms hold. You should check the rest. Okay, so this was like very simple vector space here. And this other vector space, this fx thing, this is just the set of polynomials in the variable x with coefficients from our field. So for example, r adjoin x would just be, would consist of things like let's see, I don't know, negative 2x plus 3, 4x squared minus 8x plus 900, stuff like that. So polynomials in the variable x are members of this set, of this vector space, and you should check the axioms yourself. Is it true that any two polynomials in x is again going to be a polynomial in x? Yeah, definitely, for sure. Is it closed under scalar multiplication? Most definitely. Do polynomials commute? When we add them up, can we reverse the order where we add them? Yeah, definitely. So check all of these things. They're pretty obvious, pretty trivial to show, but just for extra practice, you should verify the axioms here. Okay, so this is theorem 1.25 in the book, unique additive identity, and it says that every vector space has a unique additive identity, so there's only one of them. And to think of a simple example of this, you can think of the real numbers being a vector space over the real numbers. So scalars are real, vectors are also real numbers. The only additive identity is 0, is the number 0. There's no other number, so that when you add it to itself, you get the same number back. Like, it's only 0. So we're going to prove this in general. And the way that we're going to start it is we're going to suppose that there is another additive identity. So let's suppose there are two additive identities. Zero and 0 prime. And again, I'm just using the little arrow over there to show that these aren't necessarily the number 0. Like, it's a vector, right? Because our vector space can be many dimensions. So anyway, okay. So suppose that there are two. We want to show that these two have to actually equal each other, and thus there's only one additive identity. Okay, so we know that 0 prime is equal to 0 prime plus 0. Why is this? So why does this equal this? Well, because we assumed that 0 was an additive identity. So we take any vector, okay, in this case 0 prime, we add an additive identity and we get itself, okay? So that's because 0 was assumed to be additive identity. All right, and so this is going to equal 0 plus 0 prime. Why were we allowed to go from this step to this step? Well, because we're in a vector space and two vectors in a vector space commute, right? They commute over addition. So this is because of commutativity. And finally, what does this equal? Well, this is just going to equal 0. And why is this? Because we assume this guy was an additive identity. 0 prime was assumed to be additive identity. So what have we just shown? We've shown that if we have two additive identities, 0 and 0 prime, then they must be the same. They must be the same thing, right? So 0 prime is equal to 0, and we're done. So there is only one unique additive identity. There can't be two. And if there are two, then they're the same. They equal each other. Okay, so that's what that proof shows. All right, so this is theorem 1.26, unique additive inverse. This is pretty similar to the previous theorem. And the claim is that every element in a vector space has a unique additive inverse. So we're going to take a similar approach to the previous proof. And it might be tempting to do this. So might be tempting to say so we can do the other thing. We can say let W and W prime be additive inverses for V. We want to show that they equal each other. So just by the definition of additive inverses, we have that V plus W equals 0, and V plus W prime equals 0. And it might be tempting to look at these equations and say, oh, okay, well, V is equal to negative W, and V is equal to negative W prime. Set these guys equal, negative W equals negative W prime, and therefore W equals W prime. And that's wrong, because what we did in this step, it was subtle. It was subtle what we did, but we did it. And what we did was we assumed in this step right here, when we subtracted W from both sides, what we assumed when we did that is that minus W is the unique additive inverse for W, okay? And we assumed that when we subtracted minus W prime from both sides, that minus W prime is the unique additive inverse for W prime. So we can't do that because that's a circular reasoning type of thing, right? We can't use the fact that there's unique additive inverses in the proof to show that there's a unique additive inverse, right? So we can't do that. So let's get rid of this. But I just wanted to show you guys why that was not correct, because it's tempting to do that. But we're going to start the same way. So suppose W and W prime are additive inverses for V. Then we have the following. So again, we're trying to show that these two guys equal each other to show that there's only one additive inverse for any given vector V in our vector space. And again, you can think back to the real numbers. That always helps me to ground myself in more abstract settings. So think of the real numbers, -2 and 2, -4 and 4. Those are additive inverses of each other. And there's only one, right? There's only one additive inverse. Okay, so what do we have? Well, first of all, we have W equals W plus 0. Why? Well, in the previous proof, which we can use now that we proved it, 0 is the additive identity. So if we add it to any vector, we get the vector back. So this is going to equal W plus V plus W prime. And why is 0 equal to V plus W prime? Why is that the case? Why is that the case? Well, we said that W prime is the additive inverse for V. That's why that's true. That's why we could go from step 1 to step 2. All right? All right, now we can say what? Well, we can move parentheses because vector addition is associative. So we can say, well, this is the same thing as W plus V plus W prime on the outside. And again, this is just associativity. Okay. By commutativity, we can say that this guy right here is the same thing as V plus W. So this is V plus W prime. Commutativity. Okay, and we assumed that W was an additive inverse for V. So V plus W is going to be 0. So this becomes, right here, this becomes 0 plus W prime. You can do extra step for commutativity if you want, but I think it would be perfectly fine to just say, okay, well, 0 is the additive identity, 0 plus anything is itself, so this is just going to be W prime. And therefore, W has to equal W prime, so each additive inverse is unique. So here we have some notation from the book, 1.27. So let V and W be vectors in our vector space, capital V. Then negative V denotes the additive inverse of V, and V minus W is just is defined to be just what you'd expect it to be, W plus minus V. So here's 3 more theorems from the book. I'm not going to prove them. I encourage you guys to do that, and you can check your solutions with the book. But we are going to use these in some exercises in 1B. So I'm just going to state them. First one is 1.29. You have a number 0 times a vector. That's going to be 0 for every vector in your vector space, just like we'd expect that to be true. Theorem 1.30, a number times the vector 0 is 0. Now, if you want to, be super clear with this, you can put the little arrow over the 0 to say that is a vector 0, and then this guy is also the vector 0. And then finally, theorem 1.31, number -1 times a vector is what you would expect. -1 times V is negative V for every vector in our vector space, capital V. So let's go ahead and do some exercises. As usual, I encourage you to pause the video, try these out on your own, and then once you have formed a solution or something of a solution, you can check with the video, or I'm sure there's other solutions online somewhere. So, all right, so let's say we have a number A in our field F. We have a vector in our vector space V, and we have the equation A times V equals 0. We want to prove that A is either 0 or V is equal to 0. So let's do our proof. Okay, so we have 2 cases, right? So either A is 0 or it's not 0, right? A is 0 or it's not 0. So if A is 0, then we're done, right? Because that was the conclusion. It said that if A is in our field and V is a vector, A V equals 0, then either A is 0 or V is 0. If A is 0, well, that's it. that we're done. So one of the two things are true that needed to be true. So that's our first case, if A is 0. And the second case is if A is not 0. So suppose A is not 0. Well, A is in our field, and one of our field axioms, which you should Google if you're not familiar with the field axioms, but it's basically just common sense. It's like what you would think would be true with things in a field and your real numbers and the complex numbers. One of the field axioms says that every number in a field has a multiplicative inverse. So any non-zero number in a field has a multiplicative inverse. So since we're in a field and it's not 0, it has an inverse, right? It has a multiplicative inverse. And, okay, so suppose A is non-zero, then A has a multiplicative inverse. Field axioms. That's how we know that. And we'll call it A to the negative 1. Now, you might be tempted to say it's 1 over A, but our field might not necessarily be the real numbers, right? We know that in the real numbers, the multiplicative inverse of A is 1 over A because A times 1 over A is 1. So these two are multiplicative inverses of each other. But we don't know that we're working in the field of real numbers. So we're just going to denote it as A to the negative 1, just in case. So we have the following. The equation that was given to us by in the hypothesis was AV equals 0. So we have AV equals 0. Now, if I multiply both sides of this equation by the multiplicative inverse, A to the negative 1, I get A to the negative 1 times AV is equal A to the negative 1 times 0. So what can we do? Well, by associativity, we can move the parentheses and change A to the negative 1 AV to parentheses A to the negative 1A V equals A to the negative 1, 0. Now we know that this is 1, right? And so I'll write here how we knew how to do this. This is associativity. And I mean, if you really want to get crazy, you can say above this, you can say, well, how did we know that we could multiply A to the negative 1 on both sides? This is just the multiplicative property of equality. We can do the same thing to both sides of an equation. And we know that it exists because of this spiel here. Okay, so I'm justifying everything here. Now, A inverse times A, of course, is going to be 1. And we just know this by the field axioms. Okay. Now, negative 1 times a vector in our vector space. 1, this is the multiplicative identity condition. So 1 times V is V. So this is we went from here to here by the multiplicative identity from vector spaces. And negative 1 times 0, well, what did we say here? We said that a number 0 times a vector is going to be 0. But we also, know from the field axioms that A inverse, if we're thinking of it as a vector in our field, over our field, okay, so vector space over our field, then a number times 0, of course, is 0, right? Something in our field times 0, of course, is going to be 0. And that's just from the field axioms. So this is going to be equal to 0. and we are done. We are done because we assumed that, so we had two cases, right? We either have A as 0 or it's non-zero. And in the first case, when A was 0, the proof was done because we wanted to show that A had to be either 0 or V was 0. So if A was 0, we're done. We then assumed that A was not 0, and then we concluded from A not being 0 that V had to be 0. All right, so we are done that problem. Okay, so this is number 3 from the exercises in the back of 1B. Suppose we have two vectors in our vector space. V, W are in our vector space, capital V. Explain why there exists a unique x, so a unique vector in V, such that V plus 3x equals W. Okay, so we need to show two things. We need to first show that such an x exists. So we need to show that an x exists in our vector space to satisfy this. And then we need to actually show that x is unique. Okay, so we need to show existence and uniqueness. So I'm going to do some scratch work because we want to first find out what this x is, this vector x actually is. So we're given this equation V plus 3x equals W. And what I can do is I can isolate x in this equation. I know that V and W, since they're both vectors in a vector space by assumption, they have additive inverses. So what I can do is I can, I can subtract V from both sides, or I can add the additive inverse to both sides if you like thinking of it like that better. So we get that. So we get 3x equals W minus V. And then we can divide both sides by 3. So x is equal to, and I'm going to write it like this, 1/3 times W minus V is the same thing as dividing the whole thing by 3. So that's x, and does such an x exist in this vector space? And the answer is yes. Why is that? I'm just going to talk about why this is, why x is actually in V. Well, we assumed W was in V, right? We assumed that. We also assumed that V is in V. Since V is in V, its additive inverse is in V. And since capital V is a vector space, the sum of any two things in a vector space are in that vector space. So this guy is definitely in capital V, okay? W minus V is definitely in capital V for those reasons. And remember, Axler says, I think in the first chapter, that our field that's lurking in the background, unless otherwise mentioned, is going to be the real numbers or the complex numbers. So our scalars are either going to be real numbers or complex numbers, and 1/3 is in both of those things. You can just think of it, the scalars coming from the reals. But anyway, 1/3 times a vector in our space is also going to be in that space because it's closed under scalar multiplication. Therefore, x is definitely in V. So we can start our proof off by saying let x equal 1/3 times W minus V. And we just said why that is okay to write that. X is in capital V because of the reasons I explained. This is in capital V by closure of addition. 1/3 times this is in capital V by closure under scalar multiplication. So if x is going to be equal to this, then we have the following. then, and we know this is going to be true because of our scratch work off to the side, we have v plus 3 times x, so that's 1/3 w minus v. Well, if we simplify this, again, distributive properties work. We're working with stuff in the vector space. Well, if I simplify the inside, I get v plus 3 times 1/3 w minus 1/3 v. Simplify further, giving me v plus w when I distribute that guy in, and then minus v, right? Distribute that guy in. Well, that equals w, okay? So such an x exists, so that when I plug it into my equation, I do indeed get w. So that's cool. Excellent. Okay, now we need to show that this is unique. All right, so we claim that this x is unique. Okay, so we have the following. We have v plus 3x is equal to w. All right, and so what I can do is I know that w is in my vector space. It has an additive inverse, so I can subtract w from both sides, giving me v plus 3x minus w is equal to 0. And then I can divide everybody by 3, giving me, and then, by commutativity, I can rearrange these, giving me v minus w over 3 plus x equals 0. So x has to be unique because it is the additive inverse for this vector in capital V, right? This is definitely in capital V because, again, little v is in there, negative w is in there. Remember, additive inverses. The sum of any two vectors is in that space, and then scale it by 1/3, and it's still going to be in that space. So x is going to be the unique additive inverse. We prove that additive inverses for any vectors are unique because this equation v minus w over 3 plus x is equal to 0. So x must be the unique additive inverse for v minus w over 3, and we already argued why that was in capital V. All right, so we've shown that x exists such that this equation holds true, and we've also shown that x must be unique. Okay, so this is number 6 from 1B. It's kind of a weird question, but let's tackle it and see where we get with this. Okay, so let infinity and negative infinity denote two distinct objects. Who knows what they are? Neither of these objects are in the real numbers. And then it says define an addition and a scalar multiplication on the real numbers union with this object infinity, union with this object negative infinity. So specifically, we define the sum and product of two real numbers as usual. Okay, so that's one thing. The space that we're considering is the real numbers adjoin two different objects, adjoin this object infinity and adjoin this other object negative infinity. We don't really know what these are, but that's what we're defining the space to look like. And of course, real numbers, any two real numbers, when you add them, is a real number. Scalar multiplication holds, all that stuff. But we need to define what it means for multiplication and addition with these new objects. So that's what this is saying right here. This says t times the first object infinity is equal to negative infinity if the real number is less than 0. So like for instance, if you said negative 1 times infinity, since negative 1 is less than 0, your answer would be negative infinity. If you had 0 times infinity, your answer would be 0. If you had a positive number times infinity, your answer would be infinity. So 3 times infinity is infinity, etc. We define multiplication of a real number by negative infinity in a similar way. So, if you have like negative 3 times negative infinity, that's positive infinity, and so forth. So that's how we define multiplying real numbers by these new objects, infinity and negative infinity. And then Axler puts some additional criteria down here. He says, okay, if I take a real number and add infinity to it, that those two objects commute, the real number t and infinity, they commute, and it's going to equal infinity. Infinity plus infinity is infinity. Negative infinity plus negative infinity is negative infinity. A real number plus negative infinity it commutes again, negative infinity plus a real number. And then infinity plus negative infinity equals 0. And I think that he wanted to put negative, I think he also wanted to put negative infinity plus infinity. Well, actually, let's just put it like this. Also equals 0. I think that he did want to put that in the book. It might be an error, but yeah, so this is how we're defining the addition and the multiplication. And I know it looks a little crazy, but we apply the same logic to see if this space R union with these two new objects is a vector space over R. So scalar multiples are R. And we're going to explain. So first of all, closure under addition. So closure under addition and scalar multiplication. Is this true? Well, definitely for the real numbers, right? Like in this space, it's including all the real numbers plus two additional numbers. When we add any two real numbers, of course, it's still going to be in this set because it's still going to be a real number. Same thing with scalar multiplication. We just have to kind of worry about the infinity stuff. But it turns out that we're okay there because it says, hey, if I take a number in my set, a real number t, and add infinity to it, I'm still going to be in the set, right? And if I take a real number and add negative infinity to it, I'm still going to be in the set. Negative infinity, infinity, and all the real numbers are going to be in the set. So closure under addition is good, and we also have these guys show closure under addition as well. These two objects are still going to be in the set. These two objects added are still going to be in the set. And these two objects added are still going to be in the set. 0, of course, is a real number. So closure under addition is awesome. Good. Great. What about scalar multiplication? So remember, our scalars are the real numbers. Of course, as I mentioned, the real numbers are closed under scalar addition by the real numbers. But what about infinity and negative infinity? Yeah, that's okay too because of these. These things prove closure under scalar multiplication. If I multiply infinity or vector infinity by a scalar, well, it's either going to be negative infinity, 0, or infinity. All three of these are in our vector space. So we're good on that front. And we're also good right here. If we multiply a vector negative infinity by a scalar t, we're still going to be in the set in any case. Infinity, 0, or negative infinity. So that definitely works. Commutativity. Okay. So because I'm adding this last condition here. I think commutativity is okay. I think Axler meant to put this last condition here, and he didn't. Because, because if he didn't have that, then technically we couldn't say that the vector's commuted. But we're going to just assume that commutativity is satisfied. And again, this is commutativity over addition. So, he says explicitly here, t plus infinity is equal to infinity plus t. In the definition, commutativity is satisfied. And same thing up here. Take that other object, negative infinity. T plus negative infinity is negative infinity plus t. These two objects commute as do these, and these commute. Because I added in that extra condition there. So we're just going to say, okay, commutativity is cool too. He may not have meant to put this in, but I'm thinking he did just because all of the other cases are satisfied. What about additive identity? Yes, because 0 is the additive identity. We know that for real numbers, but it also works with infinity and negative infinity, right? Because up here, if we plug in 0 for t, 0 plus infinity is infinity plus 0, which is infinity. That works. So yeah. And same thing over here. 0 plus negative infinity is negative infinity plus 0 is negative infinity. Alright, cool. Additive identity is good. Let's see. Additive inverse. Well, we know in the real numbers, we know what additive inverses look like. 2 and negative 2, 4 and negative 4. And by the definition of these new two objects that were introduced, it turns out that infinity and negative infinity are additive inverses of each other, just from those definitions, because when you add them together, you get 0. So that's cool. Multiplicative identity is also included in the definition. What about associative? Okay, so we're going to have an issue with associativity. You should pause the video to see why. Like, try to investigate on your own. Remember that associativity can fail if we have A plus B in parentheses plus C not equaling A plus B plus C. So and A, B, and C are vectors in our space. Now, in our space is going to be all the real numbers with two additional objects. We know that the real numbers definitely satisfy associativity, but the two additional objects are not going to, because if we let A equal infinity and B equal infinity and C equal negative infinity, let's see what we get. Is this equal to A, again, was infinity, plus B was infinity, plus C was negative infinity? Did these equal each other? Well, no, right? Because by definition, infinity plus infinity is infinity. That's by definition. So this is infinity plus negative infinity. Again, by definition, infinity plus negative infinity is 0. So on the right side, we have 0 over here as well. So we have 0, is this equal to infinity plus 0 is infinity, and that's not true. So it fails associativity, therefore it's not a vector space. And you should check the distributive property. It fails that as well. this is not a vector space. If it fails at least one, it's not a vector space, and it fails associativity, and it also fails the distributive properties. It doesn't need to fail both. It could just fail one and not be considered a vector space, but yeah, that's the idea. Alright guys, I hope you enjoyed this video. Thanks for watching, and I'll see you guys in the next video about subspaces.